A single particle, a detector pointed at it, and the moment the measurement fired, the particle responded before it was touched. Scientists have run this experiment thousands of times, and it happens every single time. Looking changes what is there. We will travel through the double slit, into entanglement, through the eraser that rewrites past choices, and right up to the edge of what reality even is when nobody is watching. If you enjoy the journey, subscribe. There is nothing like this anywhere else. Now, close your eyes and picture the smallest thing you can imagine. Open them. We begin. A scientist pointed a detector at a single particle, and the particle changed its behavior before being touched. That sentence sounds like a mistake. It sounds like something went wrong in the lab. But it happened. And it kept happening, every single time. No matter who ran the test, no matter what equipment they used, no matter how carefully they built the setup to avoid disturbing anything, the particle responded to the act of looking, before contact, before any physical force reached it. To understand why this is so strange, you first need to understand what scientists expected. In ordinary life, looking at something does nothing to it. You stare at a basketball sitting on the floor. The basketball stays still. Your eyes do not push it. Light bounces off the ball and travels to your eye, and the ball has no idea any of this happened. That is how we expect the world to work. Objects exist. We see them. They are unchanged by our seeing them. Physics was built on that idea for 300 years. Isaac Newton wrote the rules, and the rules said reality was solid, predictable, and completely independent of who was watching. A planet moves in its orbit whether or not a single human being ever looks up at the sky. A rock falls whether or not anyone sees it fall. The universe did not need an audience. Then quantum mechanics arrived, and the audience turned out to matter. In the 1920s, physicists started probing objects far too small to see electrons, photons, individual particles of matter, and light. And what they found broke every rule Newton had written. At that scale, particles did not behave like tiny rocks. They behaved like something that had not decided what it was yet. They spread out across space like ripples on water, existing in many places at once, carrying multiple speeds simultaneously. They were blurry, uncertain, unresolved, and then something happened to them. They were measured. The instant a detector registered a particle's position, all of that blur collapsed into one specific point. The particle went from being everywhere at once to being exactly here, with a definite speed and a definite location. And crucially, the act of measuring had made that happen. The particle did not have a definite position before the measurement. The measurement created the definite position. This is not a trick of language. Physicists built mathematical equations to describe it, and the equations agreed. The particle genuinely was not in one place before you looked. Looking put it there. Think about what that means for a second. Every particle of matter in your body, in your chair, in the wall behind you, all of it obeys these rules at the smallest scale. The solid, stable world around you is built from a foundation that only snaps into focus when measured. Beneath ordinary reality is something looser, stranger, and far less certain than anything you were taught in school. Scientists spent decades arguing about whether this could really be true. Surely there was some hidden information they were missing. Surely the particle had a definite position all along, and the measurement was just revealing it. The universe could not actually be that weird, but the universe is exactly that weird. Experiments kept saying so, louder every decade. The physicist Richard Feynman once called what you are about to see the only real mystery in quantum mechanics. Everything else, he said, flows from a single experiment, one setup, one result, one impossibility that science has confirmed thousands of times and still cannot fully explain. What comes next started in 1801, in a room lit by a beam of sunlight, with a man who thought he was just studying light. Thomas Young did not intend to revolutionize physics. He was a doctor, a linguist, and a part-time physicist who had already helped decode Egyptian hieroglyphics by the time he turned his attention to light. In the early 1800s, the biggest argument in science was simple. What is light made of? Isaac Newton said particles, tiny bullets of light fired from a source, traveling in straight lines. It made sense. Light cast sharp shadows. It bounced off mirrors at clean angles. Bullet-like behavior all around. Newton's reputation was so enormous that most scientists would not dare disagree with him. Young dared. He suspected light was a wave, like a ripple spreading across water, and he had a clever way to prove it. Waves do something particles cannot. When two waves meet, they interfere with each other. Where two wave crests overlap, they combine into a bigger wave. Where a crest meets a trough, they cancel each other out completely. If he could force two beams of light to overlap and find that exact pattern of bright and dark bands, he would know light was a wave. So he built his experiment. He let a narrow beam of sunlight pass through a card with two tiny slits cut side by side, close together. On a screen a few feet away, he watched what appeared. And what appeared was extraordinary. Bands, alternating stripes of bright light and complete darkness, spread across the screen in a perfect pattern. Exactly what two overlapping waves would produce. Light had cancelled itself out in some spots and reinforced itself in others, the way ripples in a pond do when two stones are dropped close together. Newton was wrong. Light was a wave. The scientific community mostly ignored him. Disagreeing with Newton in England at that time was professionally dangerous, and Young's paper was torn apart by critics. He moved on to other things. But the experiment stayed behind, quietly correct, waiting. Over the next century, physicists confirmed Young's result again and again. Light was a wave. Case closed. Then quantum mechanics arrived and reopened everything. Because when physicists repeated Young's experiment using individual particles sent one at a time a single photon fired through the two slits, something impossible happened. The particle should have gone through one slit or the other and landed in one of two spots on the screen. That is what a particle does. Instead, over thousands of individual shots, the particles built up exactly the same interference pattern that Young's waves had made. A single particle, going through both slits at once, interfering with itself, arriving in a spread of locations that only makes sense if the particle traveled as a wave. Each individual dot on the screen seemed random, but together, across thousands of shots, they formed the wave pattern. The particles somehow knew where other particles had landed before it. Or rather, the particle had spread out like a wave, passed through both slits simultaneously, and interfered with its own two halves before landing. Young had accidentally built the most important experiment in the history of physics. He just did not know it yet. And the strangest result was still hidden, waiting for someone to add one small piece to the setup, a detector. Picture a particle as a coin spinning in the air. While it spins, it is neither heads nor tails. It is both, simultaneously, in a kind of flickering in-between. The moment it lands, and you look at it, it becomes one or the other. Before the landing, asking which side is up is a question with no answer, not because you do not know, but because the answer does not yet exist. That is a rough picture of what physicists call a wave function. Every particle in the universe is described by one. The wave function is not a physical wave you can see or touch. It is a mathematical object, a probability map that describes every possible state the particle could be in, all at once, each with a certain likelihood. The particle does not secretly have one real position and you just do not know which one. The wave function describes something genuinely spread out, something actually existing across many possibilities at the same time. When you measure the particle, the wave function collapses. All those spread out possibilities suddenly snap into a single definite outcome. The particle, which was everywhere and nowhere in particular, becomes right here, at this exact spot, with this exact speed. And here is the critical word, when. The wave function collapses when you measure it. Before measurement, the particle does not have a definite position. After measurement, it does. The measurement is what forces reality to choose. This is so strange that many of the physicists who discovered it refused to believe their own equations. Albert Einstein spent years trying to find a way around it. Erwin Schrödinger, who actually wrote the equation that describes the wave function, found the implications so absurd that he invented a famous thought experiment to show how ridiculous they were. Niels Bohr, who accepted the theory most fully, once said that if quantum mechanics did not shock you, you had not understood it. The wave function is not a small or technical detail. It is the foundation of everything. Every atom in your body is governed by a wave function. The chair you are sitting on is held together by particles whose positions and energies are described by wave functions. Solid, stable reality is built from a layer of reality that is fundamentally probabilistic, fundamentally blurry, fundamentally uncommitted until the instant a measurement locks it into place. Scientists have measured the wave function's predictions thousands of times across thousands of different experiments. The predictions are always right, to extraordinary precision. The particle really does exist in a smear of possibilities. The collapse really does happen at the moment of measurement. The wave function is one of the most tested and confirmed descriptions of nature ever written. And yet no one knows what it actually is. No one knows if the wave function is a real, physical thing that exists in the world, or just a mathematical tool, a description of our knowledge, rather than a description of reality. That argument is still happening today among some of the smartest physicists alive. The equation works perfectly. What the equation means remains one of the deepest unsolved puzzles in science. But the strangest thing the wave function does, the thing that will make your stomach drop, happens in one specific experiment. The one Young accidentally started, now run with a single particle at a time. The wave function goes through both slits, and something is about to close one of them. Here is the setup. A source fires particles toward a wall with two narrow slits cut into it. Behind the wall is a screen that records where each particle lands. The particles are sent one at a time. One, then another, then another. Each particle is completely alone. There is nothing for it to interact with, no other particle near it. You might expect each particle to pass through one slit or the other and hit the screen in one of two spots directly behind each slit. That is what a single particle should do, but that is not what happens. After thousands of particles have been fired, one by one, the screen shows the interference pattern, alternating bands of many hits and zero hits, identical to the wave pattern Thomas Young saw in 1801. The particles have somehow spread out, passed through both slits, and organized themselves into a shape that only waves can make. Each individual particle seems to land at a random spot. The first one hits here, the second hits there. No pattern visible yet. But as the count climbs into the hundreds, then thousands, the bands begin to emerge, bright regions and empty regions, perfectly arranged. The particles have been collaborating to produce a wave pattern, even though each one traveled alone, with no partner to interfere with. The only explanation that fits is the one the wave function provides. Each particle travels as a wave of probability, spread across both slits at once. On the other side of the wall, its two halves interfere with each other, building up probability in some regions, cancelling it out in others. When the particle finally hits the screen, it collapses into one spot, landing where its wave said it was most likely to go. One particle, both slits, a wave made of probabilities rather than water. This is strange enough to stop you cold. A particle going through two holes at once is already an impossible idea in everyday terms, but it has been confirmed with electrons, with atoms, with molecules made of 60 carbon atoms, arranged like tiny soccer balls, objects hundreds of times heavier than a single electron. All of them produce the interference pattern when sent through the double slit. All of them travel as waves. And every time a scientist has stared at the result and thought, surely, if we watch carefully enough, we can catch the particle choosing a slit surely we can see which path it actually takes. If we just look closely enough, the mystery will go away. So they looked. They placed a detector beside the slits, a device sensitive enough to register which slit each particle passed through. Just a detector. No other change to the experiment. Same particles, same slits, same screen. The interference pattern vanished. The particles started landing in two clusters, one behind each slit. Exactly as a ball rolling through a gap would, the wave behavior disappeared entirely. The moment the experiment was set up to record which path each particle took, the particles stopped traveling as waves. No one touched the particles. No one redirected them. The only thing that changed was the presence of a detector information about which slit, and the universe responded. Whoever first ran this test must have stared at the screen for a long time. The detector was not loud. It was not intrusive. It was a quiet little device placed near the slits, designed to register a faint signal when a particle passed by. In some versions, it barely disturbed the particles at all. In others, it detected by interacting with a second particle entangled with the one going through the slits, a way of finding out path information without ever touching the original particle directly. The interference pattern vanished every time. This result has been replicated in labs around the world for decades. Physicists have designed the most careful, elaborate versions of this experiment in history, trying to make the detection as gentle as possible, hoping to catch the wave behavior surviving. Every version tells the same story. If the experiment could, in principle, reveal which slit a particle took, even if no one actually looks at that information, the wave pattern disappears. Let that land for a moment. Scientists have run experiments where the which path detector was hooked up to a recording device, but no human ever read the recording. The wave pattern was still gone. The particle behaved as a particle, even though no conscious mind ever learned which slit it chose. The particle responded to the possibility of being known. In other experiments, physicists recorded the which path information and then erased it, immediately destroyed it before anyone saw it. The wave pattern came back. The act of erasing the information restored the quantum behavior. Reality seems to depend not on what anyone knows, but on whether the information exists at all, anywhere, in any form. You can think of it this way. Imagine walking into a room where two doors are open. If no one can ever tell which door you walk through, you somehow go through both. If there is any record of your path, a camera, a footprint, anything, you go through one. The particle version of this is not an analogy. It is literally what happens. Scientists have a technical word for why the wave pattern vanishes: decoherence. When the particle interacts with a detector, it becomes entangled with the detector's state. The quantum wave now includes the detector in it. The particle and detector become one combined system, and the interference between the particle's two possible paths gets scrambled by the detector's many possible states. The wave does not exactly collapse the way a soap bubble pops; it leaks into the environment. The pattern smears across so many possibilities that it becomes impossible to observe. But the deeper reason stays contested. Physicists agree on the math. They do not agree on what the math means. Some say the wave really does collapse. Some say it does not. Every possibility continues to exist, and the detector just registers one of them in our branch of reality. Some say the question itself is meaningless, and all we can ask is what any experiment will show. The mathematics works either way. The mystery stays either way. What is certain is this: adding the detector changes what the particle does. The particle responds to the setup it finds itself in, and the setup determines whether a record of its path could ever exist. Everything in the next several chapters is a variation on this one result, each version stranger than the last. When people first hear about the observer effect, they usually picture a scientist in a lab coat staring very hard at a particle. The idea that consciousness might be collapsing quantum waves is appealing. It sounds deep. It sounds meaningful. It suggests that the mind has a special place in the fabric of reality. Physicists mostly say, that is not what observer means. and the correction makes everything stranger. In quantum mechanics, an observer is anything that interacts with a quantum system in a way that records or could record information about it. A detector counts as an observer. A photon bouncing off a particle counts as an observation. A molecule of air colliding with an electron counts as an observation. The environment itself, the random motion of particles around any quantum system, is constantly observing, constantly measuring, constantly forcing quantum superpositions to behave more like classical objects. You do not need a mind. You do not need a brain. You do not even need a machine. Any physical interaction that carries away information about a particle's state acts as a measurement in the quantum sense and begins to collapse the wave function. This is, in some ways, a relief. It means quantum mechanics is not claiming that human consciousness runs the universe. The math describes a physical process, not a mental one. Particles are not waiting for you specifically to look at them. But in another way, this makes things much worse. If any physical interaction counts as measurement, then particles in the ordinary world are being measured constantly, from all directions, by air molecules, by photons from the sun, by stray vibrations, by everything. That is why large objects like basketballs and people do not visibly display quantum interference. They are being measured so relentlessly by so many things that their quantum wave functions collapse almost instantly into something that looks classical. They appear to have definite positions and definite velocities because the environment around them is hammering them with measurements thousands of times per second. This process, the environment measuring a quantum system and destroying its superposition, is called decoherence, and it happens faster for larger objects. A lone electron in a vacuum can maintain its spread-out wave function for long enough to produce interference in an experiment. An electron in open air gets measured by surrounding molecules in a tiny fraction of a second. A grain of sand gets measured so fast that its quantum behavior is completely invisible. A human being is in classical reality so overwhelmingly that the idea of a person being in superposition is effectively impossible under normal conditions. So, the reason your world looks solid and certain is not that quantum rules stop applying. The rules always apply. The reason is that the environment around you is acting as a constant measuring machine, collapsing quantum possibilities into classical facts before you ever get to see them. The universe does not need you to look. It is already looking, everywhere, all the time, through every particle in it. And yet something remains that no amount of decoherence can explain. The story of what happens the moment before decoherence begins. The moment when a wave function sits in superposition, unobserved, unentangled, spread across space like a ghost. What is the particle doing then? That question leads somewhere that makes even professional physicists uneasy. Imagine flipping a coin and then placing a box over it before you see the result. In ordinary life, you would say, I do not know if it landed heads or tails, but the coin definitely landed on one side. The result exists. I just have not seen it yet. Quantum superposition says something completely different. Before you open the box, before any measurement is made, the coin is in both states simultaneously. Heads and tails, stacked on top of each other in reality, each existing with a certain probability. The coin has no face until measurement forces it to choose one. That is the radical claim, and the experiments back it up. An electron has a property called spin. Think of it as a tiny internal compass needle that can point either up or down. Before you measure which way it points, the electron exists in a superposition of both directions. When you measure it, it snaps to one. But here is the critical piece. The direction it snaps to is genuinely random, governed only by the probabilities in the wave function. There is no hidden information ahead of time that determines the result. The universe rolls a weighted die at the moment of measurement. Physicists know this because of what happens when you rotate the measurement. If you measure the electron's spin in one direction and get up, then immediately measure it again in the same direction, you get up again, consistent, as expected. But if you rotate your detector and measure in a different direction, the result is random all over again, as if the first measurement never happened along that new axis. The electron had no pre-existing value along the new direction. It had to choose fresh. This has been done with electrons, photons, and atoms in experiments so carefully controlled that hidden variable explanations, the idea that particles secretly know their outcomes in advance, have been ruled out. The superposition is real. The randomness is fundamental. Now, stretch this concept. A single electron in superposition is already strange enough, but superposition applies to everything the electron does: its position, its momentum, its energy. Every physical property it has exists in a spread of possible values until measured. The electron is genuinely everywhere in its probability cloud at once, existing at every allowed energy simultaneously, until an interaction pins one value down. Scale this up. An atom contains electrons in superposition. A molecule contains atoms. In lab experiments, scientists have now sent molecules made of 2,000 atoms through double-slit setups and seen interference. Objects with enough atoms to be considered chemistry, behaving as quantum waves. The line between the quantum world and the everyday world is not drawn where most people assume, and superposition can link particles together. Two particles can become what physicists call entangled, their superpositions intertwined, so that measuring one instantly determines something about the other, regardless of how far apart they are. That consequence will be examined closely soon. But first, there is a man who stared into the heart of superposition and found something that felt like an insult to science. Werner Heisenberg looked at the act of measurement itself and discovered that looking does not just affect what a particle does. Looking permanently destroys something you can never recover. Werner Heisenberg was 25 years old in 1927 when he made the discovery that would define him. He was working in Copenhagen, Denmark, deep in the swamp of strange equations that were trying to describe how particles behaved at the atomic scale. And he noticed something in the mathematics that no one had spotted clearly before. You cannot know both the position and the speed of a particle at the same time. Not because your tools are imprecise, not because your instruments are clumsy, because the universe does not allow it. The more precisely you pin down where a particle is, the more completely you destroy information about how fast it is moving. The more accurately you measure its speed, the more blurry its location becomes. This is not a measurement problem, it is a reality problem. Here is the physical reason. To measure where a particle is, you need something to interact with it, typically a photon of light. A high-energy photon with a very short wavelength gives you a precise position measurement. But when a high-energy photon hits a particle, it kicks the particle hard, scattering it in an unpredictable direction. You now know where it was, but its new speed is unknown. Use a low-energy photon instead, and the kick is gentler. The speed stays more defined, but the long wavelength of a low-energy photon is too fuzzy to pinpoint position precisely. There is no compromise that beats both at once. Every improvement in position measurement causes an equal and unavoidable loss in momentum precision. The numbers bear this out exactly. Physicists calculated the minimum possible combined uncertainty in position and speed, and found it is always at least a specific small constant Planck's constant divided by 4 times pi. This value is so tiny it is invisible for anything the size of a baseball. A baseball's uncertainty in position, imposed by Heisenberg's principle, is 1 billion times smaller than a single atom. You will never measure the effect on a basketball, but for an electron, it is everything. An electron's uncertainty covers a space roughly the size of the atom it sits in. The electron does not have a precise location within the atom. Its position is fundamentally smeared. This is not a measurement gap, it is why the electron does not spiral into the nucleus. The uncertainty in its position creates enough spread in its momentum to keep it bouncing around stably in its orbital. The uncertainty principle is literally why atoms do not collapse. Heisenberg's insight extends to other pairs of properties too. Energy and time are linked the same way. A quantum system that exists for only a very brief moment, measured in tiny fractions of a second, cannot have a precisely defined energy. This is why particles created in high-energy physics collisions have a spread of masses rather than a single, exact mass. The universe enforces the trade-off everywhere. Heisenberg understood that this changed the meaning of measurement itself. Measuring was not passive. Measuring was violent. At the quantum level, every observation you made was an intrusion that permanently altered the thing you were studying. You could never get a clean, undisturbed picture of a quantum object. The act of seeing always cost something. This idea bothered Einstein for the rest of his life. He believed the universe had to be more orderly than this. He believed hidden information must exist somewhere, making the particles' position and speed definite even if you couldn't measure them both. He was wrong. And the experiment that proved it is even stranger than anything Heisenberg wrote. Some discoveries in science get overturned when someone builds a smarter machine. The measurement is too rough. The telescope is too small. Better equipment arrives and the mystery dissolves. Heisenberg's uncertainty principle is not that kind of discovery. It is not a limitation of the equipment. It is a limitation of reality. The mathematical structure of quantum mechanics means that position and momentum are what physicists call conjugate variables. They are deeply, irreversibly linked. The precision of one and the precision of the other are not independent measurements, they share a fixed budget. You cannot increase both. Improving one always costs the other, guaranteed by the structure of space itself. Think of it through waves. A particle in quantum mechanics behaves as a wave packet, a cluster of waves bunched together. To make the cluster very narrow, to pin down the particle to a precise location, you have to add together many waves of different wavelengths, and each wavelength corresponds to a different momentum. A narrow position requires a wide spread of momenta. A single, definite momentum corresponds to a pure, unending wave that stretches across all of space, meaning position is completely unknown. Between these extremes, every combination holds. You always have a position-momentum product that cannot shrink below a minimum value. The math forbids it. This is not a quirk of quantum theory. It is a mathematical fact about waves in general. The same trade-off appears in sound engineering, in signal processing, in how a radio antenna works. But for quantum objects, all of reality is made of waves, so all of reality obeys this limit. Scientists have spent decades designing experiments to test whether the uncertainty principle could be beaten. Could you make a measurement without disturbing the particle? Could you extract position information in some clever, indirect way that avoided the momentum kick? Every attempt has confirmed the same result. The universe enforces the limit. Every creative workaround runs into the principle showing up in a new form, blocking the path. In the 1970s, physicists proposed devices called quantum non-demolition measurements, tools that could measure one property of a particle repeatedly without disturbing it. These were built and tested. They work for specific, narrow circumstances, but they always do so by completely destroying information about the complementary property. You can measure one perfectly, the other vanishes. The budget is conserved. This is permanently disorienting. The human instinct is to believe that with enough patience, enough cleverness, enough technology, you can know anything about anything. Science has historically rewarded that instinct. But quantum mechanics found a wall, and the wall is not technological, it is mathematical. It is built into the structure of the universe, at the level where matter is made. Every particle you have ever interacted with was never fully known. Every atom in your body has a position that is inherently uncertain. You are made of objects that fundamentally cannot be completely described, even in principle. This is the normal state of matter. This is what matter is. And if that picture of particles smeared across space, unable to be pinned down, seems like it could only apply to things so small you would never notice them in everyday life, then Erwin Schrödinger has something to say to you. He built an argument that forces this quantum uncertainty into a room with a cat, and once you follow that argument to its conclusion, The question of where quantum weirdness stops begins to feel very uncomfortable. Erwin Schrödinger was not trying to be clever in 1935. He was furious. Schrödinger wrote the equation that describes how the wave function evolves over time. His equation was correct, tested, verified, used by every physicist who came after him. But the interpretation of that equation, as promoted by Niels Bohr and the Copenhagen crowd, led somewhere Schrödinger found completely unacceptable. So he constructed the most famous thought experiment in the history of physics, intending to show that the Copenhagen interpretation was absurd. Here is the setup. Place a cat inside a sealed box. Inside the box, include a tiny amount of a radioactive material, a substance where each atom has a 50% chance of decaying within 1 hour. Connect a detector to the radioactive material. If the detector registers a decay, it triggers a mechanism that releases a poison gas, killing the cat. Now wait 1 hour. According to the wave function, the radioactive atom is in superposition. It has decayed and has not decayed, both at once, until a measurement forces it to one state. The decay and non-decay possibilities are equally real and exist simultaneously. But the cat is connected to the atom. If the atom is in both states at once, then the detector is in both states at once, and the poison mechanism is in both states at once, and the cat is in both states at once. According to the Copenhagen interpretation, taken seriously and applied to large objects, the cat is simultaneously alive and dead until someone opens the box. Schrödinger found this grotesque. A cat is not a quantum particle. Surely, a living animal has a definite state, regardless of whether anyone is watching. Surely the superposition collapses somewhere before it reaches the scale of a cat. His thought experiment was a reductio ad absurdum, a proof by showing the conclusion is ridiculous that the starting assumption must be wrong. But the Copenhagen response was uncomfortable. Where, exactly, does the superposition stop? Is it the air molecules in the box that first measure the radioactive atom? Is it the detector? Is it the cat's own nervous system? Wherever you try to draw the line between quantum and classical, the same problem reappears one step earlier. The math does not include a line. The Schrödinger equation does not say, and here the superposition collapses. It just keeps going. The thought experiment exposed something physicists had been reluctant to face directly. No one knew, then or now, precisely when or why wave functions collapse. The mathematical machinery predicted outcomes with extraordinary precision. The boundary where quantum superposition gives way to definite classical reality was never written into the equations. It was assumed, argued about, and explained differently by every interpretation of quantum mechanics that followed. The cat in the box became a symbol for that unresolved question. Scientists worldwide still argue over it. Not the cat itself, everyone agrees real cats have definite states. The argument is about what the theory is telling us about reality at every scale below the cat, and about whether the theory is complete at all. The man at the center of the Copenhagen interpretation had a very specific answer to all of this, an answer that Albert Einstein called the most dangerous idea in physics. Niels Bohr was the physicist. Einstein argued with most intensely, most publicly, and most respectfully. They met at international conferences, sat across breakfast tables from each other, and spent years trading thought experiments like chess moves. Bohr was soft-spoken, patient, and almost impossible to rattle, and the answer he gave to the measurement problem was radical enough to shake the foundations of everything science thought it understood about the world. Bohr said, "A quantum system has no definite properties until it is measured. Position does not exist before measurement. Speed does not exist before measurement. The particle does not have a location. It is not hiding its location from you. Location is simply not a property the particle possesses until an interaction forces it to have one." This interpretation, known as the Copenhagen interpretation, named for the city where Bohr worked, does not just say that knowledge is limited. It says that reality itself is limited. Before observation, the particle is in a state that does not correspond to any single classical picture. The wave function is not a description of your ignorance. It is a complete description of what is real. Bohr went further. He argued that questions about what is happening to a particle between measurements are meaningless. Science could only speak about measurement outcomes. Asking what the electron was doing the moment before you measured it was like asking what a dream looked like before you were asleep enough to dream it. The question applies the wrong framework. Einstein hated this. He spent years constructing thought experiments designed to prove Bohr wrong, to show that particles must have definite properties independent of measurement. At a famous physics conference in 1927, Einstein proposed scenario after scenario, trying to sneak a violation of uncertainty past Bohr's defenses. Bohr responded to each one overnight and showed each scenario was blocked by the uncertainty principle itself. Einstein's deepest objection was philosophical. He believed in what he called local realism, the idea that physical objects have definite, real properties, independent of observation, and that nothing influences anything else faster than the speed of light. Quantum mechanics seemed to violate both. He called the theory incomplete, a useful tool, but missing something. He wrote a famous paper with two colleagues outlining the problem, arguing that quantum mechanics must be hiding a deeper reality beneath its probabilistic surface. Bohr replied that Einstein's argument assumed properties existed before measurement. Remove that assumption, and the paradox dissolves. Neither man was fully satisfied by the end of his life. Einstein died in 1955, still looking for a deeper theory. Bohr died in 1962, still defending Copenhagen. The argument itself did not end with them, but in 1964, a physicist named John Bell found a way to turn the philosophical dispute into an experiment, and the experiment could actually be run. What it found would have stunned Einstein, and it changes what we mean when we say anything is real. Albert Einstein called it spooky action at a distance, and he meant it as an insult. The idea came directly out of quantum mechanics, and he believed it proved the theory was broken. Here is the setup that troubled him. Two particles can be created together in a special way that links their wave functions. They become entangled, described by a single shared wave function rather than two separate ones. In this state, certain properties of the two particles are correlated, but neither particle has a definite value of those properties on its own. Both exist in superposition, and the superposition belongs to the pair together. Now separate the particles. Send one to a lab in New York and the other to a lab in Los Angeles, over 2,000 miles apart. As long as nothing disturbs them, the entangled state persists across that entire distance. The particles remain linked. Now measure one of them. The moment the measurement collapses its wave function and forces it into a definite state, the other particle's wave function collapses too, instantly, simultaneously, into a correlated definite state. Measure the spin of the New York particle and find it pointing up, and the Los Angeles particle will be found pointing down every single time. No matter when you measure, no matter how the particles are oriented, no matter how far apart they are, the two measurement results are correlated with a precision that classical physics cannot explain through any known mechanism. No signal travels between them. No hidden message passes from one to the other at the speed of light or below it. The correlation simply exists, as if the two particles are still the same object separated across space. Einstein's objection was immediate. Quantum mechanics must be incomplete. There must be some hidden information variables not yet discovered that determined both outcomes in advance, at the moment the particles were created. The particles carried secret instructions and only appeared to influence each other instantaneously. No information actually traveled faster than light. The universe was still local and real. This was a completely reasonable position. It was consistent with everything classical physics had ever shown, and it explained the correlation without requiring any action at a distance. The question was whether there was a way to test it. For decades, it seemed like a purely philosophical dispute. Then, John Bell did something extraordinary. He proved that if hidden variables explained the correlation, the measurements would have to obey certain statistical limits. Correlations between measurements taken in different orientations would fall within a specific range. If quantum mechanics was right, the correlations would sometimes exceed that range. The two possibilities, hidden variables or quantum mechanics, made different testable predictions. In one of the most important experimental results of the 20th century, the measurements exceeded Bell's limit every time. Quantum mechanics was right. Hidden variables of the local, realistic kind Einstein had imagined could not explain what was observed. Something genuinely strange was happening between the particles, and whatever it was, it did not obey the rules Einstein thought the universe ran on. John Bell published his theoretical result in 1964, and experimentalists immediately began trying to test it. The task was harder than it sounds. You needed a reliable source of entangled particles, detectors efficient enough to catch them reliably, and an experimental design airtight enough that no loophole could explain the result away. The first serious attempt came in the early 1970s from researchers working with entangled photons. The results exceeded Bell's limit. Quantum mechanics won, but critics pointed to loopholes. The detectors were not efficient enough, or the measurement settings were not chosen fast enough to prevent some hidden signal from traveling between the particles and influencing the outcomes. A physicist named Alain Aspect improved the test significantly in the early 1980s. His team changed the measurement settings randomly after the photons were already in flight, closing the loophole that had worried critics most. The results still exceeded Bell's limit, still consistent with quantum mechanics, still inconsistent with local hidden variables. Over the following decades, each loophole that critics identified was closed by a cleverer experiment. In 2015, researchers at a lab in the Netherlands ran what physicists called a loophole-free Bell test, an experiment that closed all the major loopholes simultaneously for the first time. The detectors were efficient. The settings were random and space-like separated, meaning no signal could have traveled between them during the measurement window. The particles were electrons, sturdier and easier to pin down than photons. The result exceeded Bell's limit by a wide margin. Local hidden variables, the comfortable, Einsteinian picture of a universe where particles carry predetermined outcomes, like dice already loaded before you roll them, are ruled out. Physics has confirmed it with enough rigor that the community has accepted it as settled. This means something deeply uncomfortable. When two entangled particles are measured, the outcomes are correlated in a way that cannot be explained by information the particles carried from the start. The correlation is real, and it is non-local. It connects across space in a way that does not fit any ordinary picture of how cause and effect work. Physicists are careful here. The correlations cannot be used to send a message faster than light. You cannot control which outcome you get when you measure your particle, so you cannot encode information to send to your partner. The non-locality is real, but cannot be weaponized into a faster-than-light communication device. Relativity stays intact, but the deeper statement stands. Einstein's dream of a universe where objects have definite properties independent of measurement, and where nothing connects across space faster than light, is incompatible with experiment. The universe is not locally real in the way Einstein required. Something else is going on. No one fully agrees on what that something is. And the next experiment makes the question even more disorienting. Two particles, one in a lab, one sent to the other side of the planet, a measurement on one, and the other responds. No signal, no time delay, no force traveling between them. The correlation simply exists. Physicists describe entangled particles as sharing a quantum state. Before measurement, neither particle has a definite spin or polarization or whatever property is being measured. Both are in superposition, but their superpositions are linked. The wave function that describes both particles at once contains information about how their outcomes relate to each other. When one collapses, the joint wave function tells you what the other must be. Distance, in this picture, does not break the connection. The wave function does not live in space the way an object does. It lives in what mathematicians call configuration space, a mathematical landscape that describes all the possible states of the combined system. When the system contains two particles, configuration space has more dimensions than ordinary space. The particles being far apart in ordinary space does not make them far apart in configuration space. The entanglement link is a feature of their shared state in that higher dimensional landscape, not a cord stretching between them through regular space. This does not mean information travels faster than light. The measurement outcomes are random. You cannot choose what result you get. So you cannot encode a message into your particle's collapse and send it to your partner. What your partner observes remains completely random until they contact you through ordinary, slower than light means and compare notes. Only then do the correlations become visible. But the correlations are real before the comparison. They exist in the results, waiting to be discovered. And they exist with no causal story that works in ordinary terms, no mechanism, no signal, no chain of events, connecting the two measurement events through space and time at a speed below light. Physicists use the phrase non-local correlations to describe this carefully, without committing to a picture of what causes them. The correlations are there. Their origin remains unclear. Some interpretations say the wave function is a real, physical object spread across space that collapses instantly everywhere when measured. Some say no collapse happens, and every outcome occurs in a separate branch of reality. Some say the question of what causes the correlation is simply not the right question to ask. What all of them agree on, the universe at the quantum level does not respect the simple, intuitive picture of space as a collection of separate local objects, each minding its own business, only affected by things directly next to them. Entanglement connects things across space in a way that nothing in classical physics prepares you for, and measurement is what activates it. The act of looking at one particle is what forces the connection to express itself visibly, which raises the next question. What happens if you do not just measure but watch, constantly, without stopping? In ancient Greece, a philosopher named Zeno proposed a paradox about motion. An arrow in flight, he argued, must occupy a single, definite position at every instant of time. At each instant, it is stationary. A series of stationary instants cannot produce movement. Therefore, motion is impossible. Zeno's paradox was resolved by calculus hundreds of years later, but physics brought it back in a new form. At the quantum level, and this time, it is not just a paradox, it is an experimental fact. The quantum Zeno effect is the discovery that a quantum system that is measured continuously cannot evolve. Watch a particle closely enough, frequently enough, and you can freeze it in its current state indefinitely. The watched particle never changes. Here is why. A quantum particle in an unstable state, say, a radioactive atom about to decay, evolves over time as its wave function slowly shifts, increasing the probability of decay. The longer you leave it alone, the more likely decay becomes. But if you measure it before significant evolution has occurred, the measurement collapses the wave function back to the undecayed state. The probability resets to nearly zero. Measure it again immediately, same result. Measure fast enough, and you trap the particle in its initial state. The decay probability never gets a chance to build. Cornell University physicists confirmed this effect in 2015, using atoms cooled to just above absolute zero, cold enough that quantum effects dominated their behavior completely. The atoms were arranged in a way that should have allowed them to tunnel through a barrier and move from place to place. Tunneling is a quantum behavior where particles cross barriers that classical physics says they cannot cross. It powers the sun and runs the components inside every modern microprocessor. The Cornell atoms should have been tunneling freely, but as long as researchers kept observing them with a laser, no tunneling occurred. The atoms stayed exactly where they were. The moment observation stopped, tunneling resumed. The quantum Zeno effect is a direct demonstration that measurement actively shapes quantum evolution. The particle does not observe the observation passively and continue on its way. The measurement reaches into its future possibilities and collapses them back, The act of looking locks the particle in place. This has practical applications in quantum computing. Unwanted evolution errors building up in a quantum calculation can sometimes be suppressed by monitoring the system frequently. The Zeno effect acts as a kind of quantum error suppression, buying time for calculations to complete before decoherence destroys the information. But the deeper implication is unsettling. Leaving something alone is not a neutral act in quantum mechanics. Choosing not to measure a system is an active choice that allows the system's wave function to evolve freely. Choosing to measure is an active choice that arrests that evolution. The observer's decision about when to look and how often genuinely determines what the particle does. The next experiment goes further still. Scientists found a way to erase information about a particle's path after the particle had already completed its journey, and when the information was erased, the past behavior of the particle changed. By the 1980s, physicists had established the basic result, adding which path information kills the interference pattern, and removing which path information brings it back. But a team, including physicist Marlon Scully, pushed the question further. What if you waited until after the particle passed through the slits to decide whether to keep or erase the path information? The quantum eraser experiment does exactly this. A source fires photon pairs two entangled photons created simultaneously. One photon, called the signal photon, goes through a double-slit setup. Its entangled partner, called the idler, carries information about which slit the signal photon passed through. When the idler is detected in a way that reveals which slit information, the signal photon's interference pattern vanishes. The signal photon behaved as a particle, not a wave. When the idler is detected in a way that destroys the which slit information, erases it, the signal photon's data reveals the interference pattern. So far, similar to the basic result. But here is the key. In the delayed choice version, the idler is detected after the signal photon has already hit the screen. The signal photon's behavior wave or particle seems to be determined by what happens to the idler later. The decision about the idler is made after the signal photon has already completed its journey. And yet the signal photon's statistical behavior matches what that later decision required. When researchers analyze only the signal photon detections that correspond to idlers whose path information was erased, the interference pattern appears in those results. When they analyze signal photon detections that correspond to idlers whose path information was preserved, the particle pattern appears. The full screen of signal photon detections shows nothing special. The pattern looks washed out. The magic appears only in the post-selected subsets, sorted by what was done to the idler afterward. This does not mean a measurement made now can change the past. The signal photon detections happen before the idler detections. You cannot know which subset to look at until the idler data comes in. No information travels backward in time. What the experiment shows is something stranger in a different way. The behavior of the signal photon cannot be assigned to a single moment in time. Its wave or particle nature only becomes defined when the full context, including what happens to its entangled partner later, is taken into account. The entangled pair is one quantum system. Asking what the signal photon did by itself, ignoring the idler, is like asking what one hand in a handshake did while ignoring the other hand. The system is defined by the whole. Most physicists interpret the quantum eraser as confirming that quantum correlations are genuinely non-local and non-temporal in ways that classical intuition cannot capture. The wave function does not respect the neat forward-marching clock that ordinary experience suggests time should follow. But John Wheeler took the logic even further. He proposed that a delayed choice could determine whether a photon had been a wave or a particle for its entire journey, even if that journey began millions of years before the choice was made. John Archibald Wheeler was one of the most creative theoretical physicists of the 20th century. He coined the term black hole. He worked alongside Einstein, and in 1978, he proposed a thought experiment so disorienting that physicists spent the next 4 decades building experiments to test it. Wheeler's delayed choice experiment begins with the double slit setup, but extends it to an almost cosmic scale of reasoning. In the standard experiment, you decide before the photon is fired whether to install the detector that collapses the wave function. Wheeler asked, what if you made the decision after the photon passed through the slits, but before it hit the screen? Could the late choice still determine whether the photon had traveled as a wave or a particle through the slits? Early lab versions of this experiment were built in the 1980s and confirmed the basic answer: yes. A detector inserted after the photon passed the slits, but before it reached the screen, still collapsed the interference pattern. The photon's behavior through the slits appeared to be determined by a choice made after the slits were already behind it. Wheeler pointed out a staggering implication. Light from distant quasars, compact, intensely bright objects, billions of light years away, can be bent by massive galaxies sitting between the quasar and Earth in a process called gravitational lensing. The galaxy's gravity acts as a kind of lens, and light from the quasar can reach Earth by traveling along 2 separate paths around the galaxy. A photon that left the quasar billions of years ago arrives at Earth having, in quantum terms, taken both paths simultaneously, behaving as a wave. If a physicist on Earth sets up a detector to determine which path the photon took, the photon behaves as a particle. The interference pattern vanishes, but the photon has been traveling for billions of years already. The choice of whether to install a detector was made here, today, on Earth, after the photon had already completed nearly all of its journey. According to Wheeler's reasoning, a decision made on Earth in the present appears to reach back across billions of years of the photon's history and retroactively determine how it behaved for its entire journey. Wheeler himself was careful about interpretation. He did not believe information could travel backward in time. He argued instead that the photon did not have a definite behavior wave or particle until the measurement was made. The question of how it traveled is simply not answerable before the measurement. The past, in quantum mechanics, does not come fully formed and waiting. It crystallizes into a specific history only when a measurement locks it down. This concept that the past is not fixed independently of observation remains one of the most debated in all of physics. Most physicists interpret the delayed choice results without invoking backward causation, but the experiments confirm that the quantum behavior of a photon cannot be assigned to a single point in its history. The full arc of its journey, from source to detector, must be treated as one undivided event. A photon that left a galaxy a billion years before Earth formed may have its wave or particle behavior set the moment a physicist here decides how to observe it. And if you feel a rising sense of unease about what reality means when no one is measuring, the next question is the one physics cannot yet answer. At the World Science Festival in 2024, the physicist Brian Greene sat 3 leading quantum mechanics researchers down on stage and asked each one the same question. What actually happens during a measurement? What causes the wave function to collapse? He got 3 completely different answers. One said decoherence, the environment measures the particle and scrambles the superposition. One said the many worlds interpretation, no collapse happens at all. Every outcome occurs in a separate branch of reality. One said it depends on the observer's relationship to the system. None of them agreed, and all 3 were experts. This is the measurement problem. After a century of quantum mechanics, the most successful physical theory ever written, physicists still cannot agree on what quantum theory is actually telling us about the world. The math works perfectly. It makes predictions accurate to more decimal places than any other theory in history. What the math means, what physically happens when a superposition meets a detector, remains unsettled. The core of the problem is a contradiction inside the theory itself. The Schrödinger equation, which governs how quantum states evolve, is deterministic. Give it a wave function at one moment, and it tells you exactly what that wave function looks like at every future moment. The equation never breaks down. It never produces anything other than a smoothly evolving superposition. Left alone, quantum systems spread and blur and interfere, following the Schrödinger equation perfectly. But measurements do not produce superpositions. Measurements produce single, definite outcomes. You measure an electron's spin and get one answer every time, a perfectly decisive result emerging from a perfectly undecisive equation. Somewhere between the wave function and the measurement result, something happens. The theory describes the before and the after beautifully. The transition between them, the actual moment of collapse, has no mathematical description inside the theory. It is simply assumed, and then a measurement occurs, is bolted onto the equations from outside, without any dynamical explanation for how or why. Some physicists say this means the theory is incomplete. Others say it means the question itself is wrong, that asking for a description of collapse is asking for something physics cannot provide. Others say collapse is real and needs a new physical equation to describe it. 13 distinct interpretations of quantum mechanics currently exist, each resolving the problem differently, each consistent with all known experimental data, none of them accepted by everyone. The honest answer, in 2026, is that physics does not know what measurement is, what your phone, your eyes, and every detector ever built are actually doing to the fabric of reality unknown. The mathematics predicts the result. The mechanism behind the result is the deepest open question in all of science, and the leading candidates for an answer point in directions that, at first glance, seem almost as strange as the problem. One of the most powerful ideas in the history of quantum physics came not from a famous name or a celebrated experiment, but from a 25-year-old physics student in Germany in 1970. Dieter Zeh was reading through the standard formulation of quantum mechanics and noticed something the field had largely ignored. No quantum system is ever truly isolated. Every particle interacts with its environment constantly. Air molecules, photons from distant sources, stray electromagnetic fields, the vacuum itself, flickering with quantum fluctuations. Every one of these interactions is, in the quantum sense, a measurement. Every one of them entangles the particle with the surrounding environment and leaks information about the particle's state outward into the world. What this means, Zeh realized, is that superpositions do not need a special measurement device to collapse. The environment collapses them automatically, constantly, whether or not anyone is watching. The wave function of an isolated particle in a lab can hold its superposition for a measurable length of time. An electron exposed to open air loses its superposition in roughly a trillionth of a second. A grain of sand, bombarded by air molecules on all sides, loses its quantum behavior so fast that no experiment could ever detect any trace of it. This process is called decoherence. It is the explanation for why your world looks classical. Every large object, your hand, a baseball, a car, is in such constant contact with its environment that its quantum superposition disperses into the surrounding world before it can ever build up into anything observable. The object's quantum possibilities are not destroyed. They become entangled with quadrillions of environmental particles, spread so thin across so many systems that retrieving them is effectively impossible. The superposition becomes invisible. The object behaves classically because anything quantum about it has leaked away into the surroundings. Decoherence is confirmed by experiment. Scientists have measured how long superpositions survive in controlled environments of different sizes and isolation levels. The predictions match. Large, warm, open objects decohere almost instantly. Small, cold, carefully isolated objects can maintain superposition for milliseconds, seconds, or longer. The environment acts as a relentless measuring machine, and the rate of measurement depends entirely on how exposed the object is to it. Decoherence explains a great deal. The classical appearance of the world, the sharpness of everyday objects, the absence of obvious quantum behavior in macroscopic life. Decoherence accounts for all of it. The environment measuring everything around us is doing the work that used to be attributed to a special act of human observation. Yet something remains that decoherence alone cannot explain. Decoherence accounts for why a superposition becomes invisible. It does not explain why measurements produce a single outcome. After decoherence, the combined wave function of particle plus environment still contains multiple branches. Every possible outcome still exists somewhere in that combined state. Decoherence says you cannot see the other outcomes. It does not say they vanish. Something else must happen, or someone must accept that the other outcomes are still real. In 1957, a graduate student at Princeton named Hugh Everett submitted a doctoral thesis that most of the physics community initially ignored and then spent decades arguing about. The thesis proposed a solution to the measurement problem so radical that its implications, taken seriously, redesigned the entire structure of existence. Everett's idea: the wave function never collapses, ever. The Schrödinger equation is always right. When a measurement occurs, the observer and the measuring device do not force the quantum system to choose one outcome. Instead, the entire system, particle, detector, lab, and observer, enters a superposition. Every possible measurement outcome occurs, and the observer splits into separate versions, one for each outcome, each version experiencing a different definite result. There is no collapse. There are only branches. An infinite, ever-growing tree of parallel realities, each one branching off at every quantum measurement, each one completely real, each one containing observers who are certain they experience the one true outcome. Under this view, called the many worlds interpretation, the universe you are living in is one branch of an enormous structure. Right now, somewhere in the branching tree, a version of you made a different decision this morning. Every radioactive atom that could have decayed or stayed stable has done both, in separate branches. Every quantum event, in every atom, in every star, in every galaxy, is constantly splitting reality into new copies. The total number of branches grows so fast that no number in ordinary mathematics meaningfully captures it. This sounds extravagant. Everett's response to that objection was precise. The extravagance is already in the Schrödinger equation. The equation says the wave function always evolves by superposition. If you take that equation seriously as a description of reality, you get all the branches. Removing them requires adding an extra rule, the collapse that has no place in the mathematics. Everett's interpretation keeps the mathematics clean and pays for that cleanliness with an infinite supply of parallel worlds. Many working physicists today take the many worlds interpretation seriously. Physicists including Sean Carroll, David Deutsch, and Max Tegmark have defended it as the most consistent reading of quantum theory. Its critics point out that the interpretation has never made a prediction that distinguishes it from other interpretations, and that the meaning of probability in a world where all outcomes occur is deeply unclear. What it offers is this: a universe where measurement creates nothing and destroys nothing. Every possible history is real. Every particle that ever existed in superposition went both ways. Every fork in the road of quantum reality produced a genuine universe. The branch you live in is one among an uncountable number, and the version of you that went the other way is just as real, just as certain of their experience, and just as unaware of yours. In 1927, at the same international conference in Brussels where quantum mechanics was being argued into its modern form, a French physicist named Louis de Broglie proposed something that most of his colleagues dismissed immediately. He proposed that particles are real, definite objects with actual positions at all times, and that they are guided through space by a physical wave that travels ahead of them and steers them. The wave passes through both slits in the double-slit experiment. The particle passes through only one, but the wave creates an interference pattern on the other side, and the interference pattern in the wave determines where the particle is steered to land. The interference pattern emerges because the wave explored both paths. The particle, following the wave's instructions, ends up in the high probability regions. Over many particles, you see the wave's interference pattern stamped onto the screen. This picture, known as pilot wave theory, or Bohmian mechanics after David Bohm, who independently revived it in 1952, gives particles definite positions at all times. Asking where the particle is between measurements is a meaningful question. It has a real answer. You just cannot measure both position and speed precisely at once because the act of measuring perturbs the wave that guides the particle, scrambling information about the other property. In pilot wave theory, the observer effect is physical and mechanical, not mysterious. The measuring device interacts with the wave, changing it. The wave then guides the particle differently. The randomness of measurement outcomes comes from ignorance of the precise initial conditions, like classical unpredictability but at a deeper level. The universe is deterministic underneath. Probability is a tool for navigating human ignorance, not a feature of reality itself. Pilot wave theory reproduces every prediction of standard quantum mechanics. No experiment has distinguished between it and other interpretations. Its cost is that the guiding wave must respond instantly to the entire experimental setup, including changes made far away, which requires a form of non-locality that makes many physicists uncomfortable. Einstein might have appreciated pilot wave theory. It gives particles real positions and real paths. It removes the special status of measurement, but it pays for that by requiring an invisible, non-local wave threading through the entire universe, responding instantaneously to everything around every particle, everywhere. The measurement problem in this picture is solved. The strangeness is just relocated. In the early days of quantum mechanics, some of the founders noticed something that felt like it could not be a coincidence. Wave functions collapse when observed. Observation, in the ordinary sense, requires a mind. What if consciousness itself was the agent of collapse? This idea, known as the consciousness causes collapse interpretation, was championed briefly by physicists including John von Neumann and Eugene Wigner in the mid-20th century. Their argument was simple. If you trace back the chain of measurement particle to detector, detector to amplifier, amplifier to display, display to human eye to brain, you never find a point where the mathematics says collapse must occur. The Schrödinger equation just keeps entangling everything. The chain of quantum interaction extends all the way up to the brain itself. If you believe collapse is real and must happen somewhere, consciousness is the only candidate left that sits outside the physical chain. The idea attracted fierce criticism. John Bell put it bluntly. Was the universe in superposition for billions of years before single-celled organisms evolved? Did it need a biology degree before it could collapse? The suggestion that consciousness requires special physics to occur, and that those physics were suppressed for the first 9 billion years of the universe's existence, struck most physicists as far too convenient. Decoherence theory later made the consciousness interpretation largely obsolete for most physicists. The environment collapses superpositions without needing a mind. Air molecules, photons, random fields, these are sufficient to explain why macroscopic objects behave classically. Consciousness is not required. Yet the idea has never fully disappeared. Roger Penrose and Stuart Hameroff proposed a version of it in recent decades, suggesting that consciousness arises when quantum superpositions in tiny structures inside neurons collapse, and that this collapse is driven by gravitational effects rather than environmental measurement. The proposal remains highly speculative. Most neuroscientists do not accept it, and most quantum physicists find it difficult to test. In 2023, a team ran an experiment designed to check whether human conscious attention measurably influenced quantum outcomes. Over 10,000 trials, they found a deviation of about 1% from expected results tantalizing, but far too small and too unreplicated to draw any conclusions from. The mainstream view is that consciousness plays no special role in quantum measurement. The hard evidence supports that view. But the question has not been put to rest with the kind of clean, definitive experiment that would end the debate. And until it is, some physicists will keep returning to the idea that the mind and the wave function are connected in a way that physics has not yet fully mapped. The word teleportation, in physics, sounds like something from a movie, but quantum teleportation is real, experimentally confirmed, and has been used to transmit quantum states across distances ranging from a lab bench to hundreds of miles through fiber optic cable. It works, and understanding what it actually does reveals something profound about the nature of information and measurement. Quantum teleportation does not move matter. A particle is not disassembled in one place and rebuilt in another. What travels is information specifically, all the quantum information describing a particle's state. Here is how it works. Two particles are entangled and separated. One stays near the sender, called Alice. One travels to the receiver, called Bob. Alice takes the particle she wants to teleport, call it the mystery particle, and performs a special joint measurement on it and her half of the entangled pair. This measurement does two things simultaneously. It collapses the mystery particle's wave function, destroying its original quantum state, and it creates correlations that are instantly reflected in Bob's particle across the distance. Alice then sends Bob a small amount of classical information, just 2 ordinary bits, through a normal channel. Bob uses that information to apply a correction to his particle. When he does, his particle is now in exactly the state the mystery particle was in before Alice measured it. The original is gone. The mystery particle no longer carries its original state. The state has been recreated, perfectly, at Bob's location. The no-cloning theorem of quantum mechanics forbids making a copy of a quantum state, and teleportation honors this by destroying the original. The state moved, the particle stayed. Every step of this process depends on measurement. Alice's joint measurement is the engine that drives teleportation. Without the measurement, nothing transfers. The collapse is not a bug to be worked around. It is the mechanism that makes the transfer possible. Measurement reaches into the quantum state, extracts its information through the entanglement link, and delivers it across space. Scientists have teleported quantum states of photons, atoms, and recently of quantum states in solid-state systems, bringing quantum networking closer to practical reality. In 2025, a Harvard team demonstrated error-corrected quantum teleportation as part of a scalable quantum computer architecture, a milestone that brings the idea of a quantum internet measurably closer to existence. And embedded in every one of these demonstrations is the observer effect. Measurement destroys the quantum state of one particle to give birth to its twin somewhere else. The act of looking, in quantum teleportation, is the act of creation. A quantum computer is, at its core, a machine that keeps particles in superposition long enough to use that superposition for calculation. Every qubit, a quantum bit, exists in a superposition of 0 and 1 simultaneously. A collection of 50 qubits is in a superposition of every possible combination of zeros and ones at the same time. That is roughly 1,000 trillion states, all existing and computing in parallel, all at once. This sounds impossibly powerful. And for certain classes of problems, it is. A quantum computer can factor enormous numbers, search vast databases, and simulate molecular chemistry in ways that would take an ordinary computer longer than the age of the universe. But the power of a quantum computer depends entirely on keeping the superposition intact throughout the calculation. The moment the qubits interact with the environment with stray photons, heat, vibrations, electrical noise, anything decoherence begins. The qubits lose their superposition. The computation collapses into a scrambled mess of ordinary bits. The result is garbage. This is why quantum computers must operate at temperatures near absolute zero in carefully shielded chambers, isolated from the surrounding environment more completely than almost any other object on Earth. The temperature used in some quantum computers is colder than the surface of deep space by a factor of 100. The engineering required to maintain this isolation is extraordinary. And here is the cruelest irony. To get the answer out, you have to measure the qubits. Measurement collapses the superposition. All those 1,000 trillion parallel states compress into a single definite output. The measurement is the only way to extract the result, and the measurement ends the quantum behavior that made the result possible. Quantum computing researchers spend enormous effort on timing this measurement correctly. Measure too early, and the computation is incomplete. Measure at the right moment, and the superposition's interference, all those parallel computation paths reinforcing each other, has steered the answer into a high probability state. The measurement collapses the wave function onto the answer. Every quantum algorithm is, at its deepest level, a choreography of superposition and interference, designed so that the wrong answers cancel each other out and the right answer survives with high probability to be found when measurement finally arrives. The observer effect is not a problem to overcome in quantum computing. It is the punchline. The whole calculation is a race between useful quantum behavior and the decoherence that measurement brings, and the art of the algorithm is making sure the answer survives the finish line. In 1984, two computer scientists named Charles Bennett and Gilles Brassard published a protocol for transmitting information that is, in principle, impossible to intercept secretly. They called it a quantum key distribution protocol, and the reason it works is the observer effect. Here is the concept. Alice wants to send Bob a secret key, a string of random bits that they can use to encrypt a message. She sends the key encoded in the quantum states of individual photons. Each photon carries a qubit of information, prepared in one of several quantum states. If an eavesdropper, call her Eve, intercepts a photon to read it, she must measure it. Quantum mechanics demands this. There is no way to gather information about a quantum state without interacting with it. And interaction is measurement. Measurement collapses the photon's wave function. Eve can read the qubit, but she cannot copy the original quantum state before measuring it. The no-cloning theorem prevents this. She must measure, which destroys the original state, and then send Bob a replacement photon. The replacement photon will not match the original quantum state perfectly. It cannot. Eve did not know which basis Alice used to prepare it, so she had to guess. Her guess was wrong half the time. When Alice and Bob later compare a small sample of their key bits through an ordinary public channel, they find errors. Errors where there should be none. The errors are the signature of eavesdropping. If the error rate stays below a threshold, the channel is clean. If the error rate exceeds that threshold, the channel has been compromised. Alice and Bob discard the key and start again. The security of this system is not based on mathematics that could be broken by a powerful enough computer. It is based on physics. Specifically, it is based on the fact that measurement disturbs quantum states. Any eavesdropper, no matter how sophisticated their equipment, is forced to interact with the photons to read them, and that interaction leaves a physical trace. The observer effect becomes the security system. Quantum cryptography is already deployed in some commercial networks and government communications in China, Japan, Switzerland, and other countries. It currently works over distances of a few hundred miles through fiber. Satellites carrying quantum keys have extended this across thousands of miles. The goal is a global quantum communication network where interception is detectable in principle by the laws of physics. The universe's most fundamental measurement rule that observation disturbs the observed has been turned into the most secure communication channel conceivable. Quantum mechanics, as it is usually taught, assumes there is an observer, a laboratory, a detector, a measuring device that exists separately from the quantum system being studied. The observer sits outside. The system sits inside. The measurement is the moment the outside reaches in. But what about the entire universe? If everything obeys quantum rules, then the universe itself must be described by a wave function. A single, all-encompassing wave function that tracks every particle, every field, every interaction across the full 13.8 billion year history of existence. This is the domain of quantum cosmology, the attempt to apply quantum mechanics to the universe as a whole. The trouble is immediate. A wave function for the whole universe has nothing outside it. There is no external observer. There is no lab standing apart from the system, reaching in with a detector. If quantum mechanics requires measurement by something external to collapse the wave function, and the universe contains everything that exists, then nothing can play the role of external observer. The universe measures itself, or nothing measures it, or the framework breaks down entirely. In the very early universe, during the first tiny fractions of a second after the Big Bang, quantum fluctuations were the dominant feature of reality. Tiny patches of space expanded and contracted randomly, governed by quantum uncertainty. These fluctuations grew as the universe expanded. They became the seeds of the first stars, the first galaxies, the large-scale structure of the cosmos. The map of the universe, today, is the amplified imprint of quantum measurement events in the first moments of existence. If the Copenhagen interpretation is right, these fluctuations only took on definite values when they were measured. But by what? At early enough times, nothing complex enough to constitute an observer existed. Protons had not yet formed. Atoms were billions of years away. The universe was a hot, featureless plasma of energy. The many worlds interpretation sidesteps this problem. The fluctuations exist in all their quantum values across different branches of the wave function, with no collapse required. Decoherence theory offers another route. The quantum fluctuations interacted with other parts of the early universe, entangling with the larger environment, and decoherence did the collapsing automatically. But the question remains philosophically sharp. The universe's current structure, the reason you exist, the reason stars burn, the reason galaxies hold together traces back to quantum measurement events at the beginning of time. Whatever performed those measurements, whatever converted the early wave function's blur of possibilities into the specific, particular universe that exists today, shaped everything that followed. This is the question that makes physicists uncomfortable at dinner parties, and it deserves a careful answer. John Wheeler spent the later decades of his career working on a concept he called the participatory universe. His argument started from standard quantum mechanics and escalated. If measurement is required to collapse a wave function into a definite state, and if the universe itself is governed by quantum rules, then at some level, the universe's definite history requires measurement. And if measurement requires observers, then in some sense, observers are not just products of the universe, they are participants in making it real. Wheeler's delayed choice argument, taken to cosmic scale, suggests something vertiginous. Every time an astronomer uses a telescope to observe light from a galaxy 10 billion light-years away, the act of observation may be settling a quantum ambiguity that has been unresolved for 10 billion years. The photon's path wave or particle, through this route or that, was not decided until the measurement happened, even though the photon set out billions of years before any human existed. If this reading is correct, the present moment actively participates in finalizing the past. Observers do not merely describe history, they complete it. Most physicists interpret Wheeler's ideas carefully. They do not take them to mean that human consciousness is cosmically necessary, or that the universe was waiting specifically for humans to evolve before anything became real. The relevant entity is any physical process that counts as a measurement which, as discussed, includes air molecules, photon collisions, and any interaction that records information about a quantum state. Life was not required, complex interactions were, but the question of whether a universe with no interactions at all, no decoherence, no entanglement, no measurement would be real in any meaningful sense, has no clean answer inside quantum mechanics. A universe described only by a wave function that never interacts with anything, never decoheres, never measures anything, would look in the mathematics exactly like a universe in superposition of every possible history simultaneously. Nothing in it would have a definite value. Nothing would be distinguishable from anything else. The universe we live in has definite structure, definite stars, definite atoms, Something produced all of that definiteness. Whether observers were required, or whether blind physical interaction was sufficient, depends entirely on which interpretation of quantum mechanics you accept. And as of 2026, that is still an open argument. For most of the 20th century, quantum mechanics was the science of the very small electrons, photons, atoms, objects so tiny that no human eye could ever see them and no classical intuition could help. Quantum behavior was exotic, distant, confined to laboratories running experiments at temperatures close to absolute zero. That picture has been steadily dismantling itself. In 2019, a team at the universities of Vienna and Basel fired molecules containing 2,000 atoms through a double-slit apparatus and observed interference. 2,000 atoms, a cluster large enough to be considered actual chemistry, not a single particle, not a handful of atoms, but an intricate organic structure built by chemists specifically to be massive enough to challenge the quantum classical boundary. The interference pattern appeared. The wave function spread across both slits. The quantum rules held. In 2026, physicists at the University of Vienna repeated the experiment with sodium nanoparticles containing between 5,000 and 10,000 atoms. Clumps of metal visible under electron microscopy, not theoretical constructions. These metallic clusters also produced interference patterns. Their positions were not fixed during flight. Their quantum states spread across distances dozens of times larger than the particles themselves before collapsing into definite landing spots. Alongside these mass records, other experiments have pushed quantum behavior into mechanical systems. Scientists have cooled tiny vibrating drums, membranes made of silicon or aluminum nitride, objects you could see under an ordinary microscope to their quantum ground states, and placed them in superposition. These are objects closer to the scale of everyday things than anything quantum mechanics has ever touched before. The boundary between quantum and classical is not a wall, it is a gradient. Objects lose their quantum coherence faster as they grow larger, because more atoms mean more surfaces for environmental interaction, more channels for decoherence to leak through. But the rules that govern atoms govern everything made of atoms. The quantum behavior does not stop. It just gets squeezed out by the environment faster and faster as objects grow. The current frontier is pushing that boundary. What is the largest object that can be placed in a genuine quantum superposition in a controlled experiment? The answer keeps growing, and somewhere along that scale, the question of where quantum mechanics ends and classical mechanics begins will have to be answered not by interpretation, but by data. There is a line somewhere, a boundary between the world where particles exist in all states simultaneously and the world where cats are definitely alive or dead and basketballs have exactly one location. Every experiment that pushes quantum behavior into larger objects is an attempt to find that line and mark it. The problem is that quantum mechanics does not include the line. The Schrödinger equation applies equally to one electron and to 1 trillion electrons arranged into a piece of metal. The mathematics makes no distinction. Superposition is superposition, regardless of how many atoms are involved. If the equation is complete, then everything should be capable of quantum behavior, and the line should not exist. And yet, the line is functionally real. You do not observe quantum interference in your coffee cup or your car. Large objects behave classically to a precision that no experiment has ever deviated from. The difference between a 2,000 atom molecule and a coffee cup about 1 trillion atoms is the difference between detectable quantum interference and no quantum interference at any accessible level. Decoherence explains this quantitatively. The decoherence time of an object, the time it takes for environmental interactions to scramble its superposition, decreases with size so steeply that a grain of sand in open air decoheres in something like 10 to the negative 30th of a second. No experiment could detect its quantum behavior because the quantum behavior is gone before any measuring device could respond. The boundary is not sharp. It is a steep gradient that falls towards zero so fast that, for everyday objects, it is effectively instantaneous. But decoherence is not universally accepted as the complete answer. Some physicists argue that the wave function must physically collapse, and that this collapse is not just apparent from interaction with the environment, but real. If collapse is real and physical, it must have a trigger. Several proposed theories say the trigger is mass. Above a certain threshold of mass or of particles involved, wave functions spontaneously collapse at a rate that grows with size. These theories make predictions that differ slightly from standard quantum mechanics for large, carefully isolated objects. Experiments are currently testing these predictions, and the Vienna nanoparticle experiments in 2026 were partly designed to constrain them. The answer where quantum weirdness stops and classical reality begins, and why is still ahead of us. What the experiments keep finding, with every new record, is that the quantum world is bigger than we thought. While physicists debate the boundary of the quantum world in laboratories, something far older than human science has been exploiting quantum measurement every moment of every day. Inside the cells of every green leaf, every blade of grass, every algae slick on a pond's surface, quantum mechanics is running an energy transfer system of extraordinary efficiency. Photosynthesis converts sunlight into chemical energy with an efficiency that defies classical explanation. In ideal conditions, the energy from a single absorbed photon arrives at the reaction center, the part of the cell that converts it into chemistry, with greater than 95% efficiency. Human-built solar panels reach 20 to 30%. The best artificial energy transfer systems struggle to beat 60%. Plants, doing this in warm, wet, noisy biological environments, do better than any human engineering. When a photon hits a light harvesting complex in a plant cell, it creates an exciton, a packet of energy that must travel from the point of absorption to the reaction center along a network of molecules. Classically, this energy would hop randomly from molecule to molecule, like a drunk wandering through a maze, losing a little energy at each step. The probability of reaching the reaction center efficiently by random hopping is far too low to explain what plants actually achieve. Experiments in 2007, confirmed and extended in 2010, showed something extraordinary. The energy travels as a quantum wave of probability, exploring all possible paths through the molecular network simultaneously. The energy samples every route at once, and the wave interference guides it toward the most efficient path. Only when it arrives at the reaction center and is captured, measured, in the quantum sense does the wave function collapse and the energy become a definite, localized chemical event. The plant is exploiting superposition to route energy more efficiently than any classical random walk could achieve. Measurement is what finalizes the delivery. The debate over the precise mechanism, whether it is purely electronic quantum coherence or a mix of electronic and vibrational effects, continues in the research literature. But the role of quantum effects in photosynthetic efficiency is now widely accepted. Life figured out how to use the observer effect to survive. Every sandwich you have ever eaten was made possible by quantum mechanics doing its work inside a chlorophyll molecule long before any physicist named it. Time feels obvious. It moves forward. The past is fixed. The future is open. You remember yesterday and not tomorrow. This is so fundamental to experience that questioning it seems almost meaningless. But quantum mechanics raises a very uncomfortable possibility. The laws of quantum mechanics, like all fundamental physical laws, are time-symmetric. Run the Schrödinger equation forward or backward, and both directions are equally valid mathematically. Nothing in the equation distinguishes past from future. The apparent one-way flow of time, the arrow of time, requires something extra. In thermodynamics, that extra ingredient is entropy, the tendency of systems to move from ordered to disordered states. We can tell that a video of eggs unscrambling is running backward because scrambled eggs have higher entropy than whole eggs. Time's arrow, in this picture, points toward increasing disorder. But decoherence adds a quantum layer to this story. When a quantum system decoheres, when it interacts with the environment, and loses its superposition, the process is effectively irreversible. Information about the quantum state leaks into the environment, spreading across so many particles that retrieving it is practically impossible. Each act of measurement, each collapse of a wave function, each quantum interaction with the environment creates an irreversible fact. It stamps a moment into reality. Some physicists argue that time's arrow is not primarily thermodynamic, but quantum mechanical. It is the direction of increasing decoherence, increasing entanglement with the environment, increasing measurement. Before a quantum event is measured, multiple outcomes coexist. After measurement, one is definite. The before and after of that transition are not symmetric. They cannot be undone. The implication is strange and deep. Time might be, at its foundation, the accumulation of measurement events. The universe gets older because more and more quantum states have been collapsed. More information has been locked into definite form. More superpositions have been replaced by facts. The past is made of collapsed wave functions. The future is made of superpositions that have not yet been measured. If this picture is right, then every measurement you have ever participated in, every photon your eye absorbed, every atom your body interacted with, was not just recording reality, it was producing time itself. You have been making measurements your entire life. Every photon that has ever struck your retina was a measurement, a quantum interaction that collapsed a wave function and created a definite event. Every breath you have taken moved atoms that were in thermal equilibrium, scattering them into new quantum states. Every step transferred energy to the ground, entangling your atoms with the floor's atoms, creating irreversible changes that propagated outward through the environment. This is not poetry, it is physics. The observer effect is not something that happens in a special laboratory reserved for scientists with expensive equipment. It happens constantly, everywhere, in every interaction between any particle and any other particle. The atoms in your body are decoherence machines. They interact with the environment billions of times per second, collapsing quantum states and locking in definite outcomes. Every decision you have ever made has been the result of physical processes in a brain made of atoms obeying quantum mechanics. Every word you have spoken has scattered photons and air molecules into new states. Every moment of your life has been a chain of measurement events, each one irreversible, each one permanently altering the state of the quantum systems around you. You cannot undo these changes. Quantum states that have collapsed do not uncollapse. Information that has leaked into the environment does not return. The past is made of locked-in measurement events, and your presence in the world has added an enormous number of them. The universe you live in is, in a real quantum mechanical sense, different from what it would have been without you at the level of individual particles and their states. The physicist's version of this is precise. Every measurement increases entanglement between the measured system and the environment. Entanglement, once created, alters the statistics of every future measurement involving those particles. The ripples from every collapse propagate outward through the web of entanglement, changing what is possible next. None of this is detectable at human scale. The effects are real and irreversible at the quantum level, but decoherence ensures they look like nothing more than ordinary thermodynamic noise at any scale you can directly observe. Yet they are there. The universe keeps a perfect record of every measurement event that has ever occurred. That record is distributed across the entangled states of every particle that has ever interacted with anything. You have been writing in that record since the moment you were born. Here is the question that quantum mechanics cannot answer, the one that sits at the center of every interpretation, every debate, every sleepless night that a physicist has spent staring at an equation that works perfectly and explains nothing. What is a particle doing between measurements? The wave function tells you the probability of each possible outcome when you measure. It does not tell you what the particle actually is between those moments. The Copenhagen interpretation says the question is meaningless between measurements. Properties simply do not exist, and asking about them applies the wrong framework. The many worlds interpretation says the particle is doing everything simultaneously in branching realities. Pilot wave theory says it has a definite position, guided by an invisible wave you cannot directly detect. Decoherence theory says the environment is constantly measuring, so the question rarely applies in practice, but does not resolve what collapse actually is. No interpretation has been experimentally distinguished from any other. Every one of them predicts the same measurement outcomes. Every one of them is consistent with every observation ever made. The mathematics is silent on which picture of reality is correct. It only tells you what you will see when you look. This is genuinely unprecedented in science. Physicists have never before had a theory that worked perfectly and yet left the fundamental nature of what it describes completely undecided. Newton's laws told you what matter was. Einstein's equations told you what space-time was. Quantum mechanics tells you what measurements will show, and for a century, that has been enough to build computers, lasers, MRI machines, solar cells, nuclear reactors, and quantum computers. The practical success is unmatched. But the question remains. Right now, before any measurement, the electrons in every atom in your body are spread across probability clouds. The photons crossing the room are wave functions, exploring all possible paths. The particles inside every nucleus are in states of quantum uncertainty, their properties not yet real in any fully defined sense. Between measurements, reality is a question held open. Measurement is the moment the answer arrives. And the most honest thing physics can say about the interval between those moments, the universe running silently between every observation, is that no one knows. The act of looking creates the answer. What exists before the looking remains, in the deepest sense, unknown. That uncertainty is not a failure of science. It is the most accurate description of nature that human beings have ever produced. And every time a detector fires, every time a photon strikes a screen, every time you open your eyes in the morning, something that was not definite becomes definite. Reality commits. And somewhere outside the reach of every measurement ever made, the rest of the wave function keeps going.